Welcome to day 2 of 10.4. Yesterday you were introduced to the identities that I'm going to ask you to fill in a few minutes. But before we do that, I'd like you to work on this warm-up. I want you to pause the video and write the cosine and sine ratios for theta. And I want you then to solve the cosine ratio for x and the sine ratio for y. All right. Hopefully you had the correct equation for x and y involving sine and cosine. Now I'd also like you to try to recall from memory these identities. So pause the video and you'll go ahead and put these in your notes. Okay, if you weren't able to do those by memory, I'm going to generate them again and just maybe give you some hints on how to memorize these. So this is a sine of an a plus b. So when I have the sign of a sum or a difference, it always begins with the sine function. And then that first term in my argument, followed by the cosine of the second term in my sum there in the argument. And then we have a match in the sign. So then I would be adding to it that other combination, sine of b times the cosine of a. So we have a match here. So I'm starting, this is a sign of a difference. I'm going to begin the other side of the expression with the sine of the first argument times cosine of the second argument. And again, we're going to have a match. And then do the other possible combination here, sine b, or excuse me, sine of b cosine a. All right, now the cosine operates a little bit differently. Again, we will start off with a cosine. So if we're taking a cosine of a sum, the other side of our equation starts with a cosine, and then it's cosine a times cosine b, and then this time we have the subtraction, so we have it be opposite. And then we take the product of the sine of a times the sine of b. And for our last one, again, we start with a cosine of a times the cosine of b, and do that opposite again. Sine of a, sine of b. All right, so we're going to do some applications of these identities. So an extension of what you learned yesterday. So what we're asked to do is, given that a cosine of s is 1 over 5 and the sine of t is 3 over 5, and both angles s and t terminate in quadrant 2, determine the exact value of cosine s plus t, sine s minus t, which quadrant s plus t terminates, and the quadrant in which s minus t terminates. What we're going to do to kick off this problem is we're going to give ourselves a visual. We are going to sketch out S and T. So we have information about the cosine of S being 1 over 5, and its S terminates in quadrant 2. So here I'm rotating around. I terminate in quadrant 2. I drop my perpendicular, and that's the sign. It is the cosine is adjacent over hypotenuse. We've got t that also terminates in quadrant 2. So we went around. We drop a perpendicular to the x-axis. Here we're talking about the sine of t is the ratio 3/5, opposite over hypotenuse. And we know this value will be positive and this one will be negative. We can very easily figure out what this is. So the formula is x squared plus y squared equals our r squared. So y squared equals 24. Y equals the square root of 24. And this time we're going to be choosing the positive, right? Because this has got to be positive in this quadrant. Y is 2 root 6. And so now we can conclude that the sine of s is 2 root 6/5. And we jump over here. I don't think we have to do as much work here if we remember that this is a Pythagorean triple, 3, 4, 5. I just have to make sure that I have that negative 4 because the cosine will be negative in this quadrant. And now we can very quickly write down the cosine of t. And now we're going to get our identity from yesterday. So the cosine of s plus t is the cosine of s times the cosine of t, subtract the sine of s times the sine of t. And now we're just going to fill in the components. The cosine of s is 1/5. The cosine of t is -4/5. The sine of s is 2 square root 6/5. The sine of t is 3 square root 5. And now we'll have a -4. Oh, I forgot my -1 here. -1. A -4 times a -1 minus 3 times a 2, which would be 6 root 6 all over 25. Tidying this up a bit, I have 4 subtract 6 square root 6 all over 25. All right, part B asks for, well, what is the value of the sine of s subtract t? So now we get our other identity. Sine of s times cosine of t subtract sine of t times cosine of s. And then we just get those components again. So our sine of s is 2 square root 6/5. The cosine of t is my -4/5. My sine of t is 3/5, and that cosine of s was -1/5. So then we will end up with -8 root 6 plus 3/25, or we may see it written 3 subtract 8 square root 6/25. All right, the next question asks, maybe I'm trying to, yeah, we'll just flip back. So now we're going to answer part C. In which quadrant does the S plus T angle terminate? Well, we need to go up and investigate our cosine S plus T. And we get that this value clearly will be negative. And this is true. The cosine is negative in quadrants 2 and quadrants 3. Now we kind of have to examine our original angles. So we had S lying in quadrant 2. So that means it would be greater than pi over 2, but less than pi. We had T in that same quadrant. So it has the same parameters or upper and lower limits. And now we want to know what S plus T will be in between, and it'll be in between pi and 2 pi. We add these together. And that would tell me that this would mean I would have to lie in either quadrant 3 or quadrant 4. And like problems that we did way back, starting this trig, we have to pick the quadrant in which shows up in both places, because we have to satisfy both of these conditions, and the only place that that will happen is in quadrant 3. And our last little question, it's asking about how about where S minus T terminates? All right, so now we need to go back and do the same type of analysis. We go up to the value of the sine of S minus T. And again, we can see this value is also negative. And this will occur in quadrants 3 and 4. But then like before, we need to investigate where our original angles were living. So we had us being in quadrant 2, so somewhere in between pi over 2 and pi. And T was in that same quadrant. However, I'm not talking about T, I'm talking about the opposite of T, right? Because I'm subtracting these. Which means when I do that, everybody's sign changes because I'm multiplying everybody by a -1. But then my inequalities also have to change. And that looks like a little funky weird. So I'm going to rewrite it so that it matches this here. So T is greater than pi or negative pi and less than negative pi over 2. And then we're going to combine these. And so I'll have a negative pi over 2. Oops. an s minus a t, and a pi over 2. So if we just kind of think about where that is, that would be me rotating up to here or down to here. So my two quadrants that are in play this time are quadrants 1 and quadrants 4. And the one that is repeated, or how we can satisfy both conditions, it's only going to happen in quadrant 4. All right. I have one more thing that I would like us to look at. Is they're going to say if an x is in between 0 and 1, greater than 0, less than or equal to 1, we want to write the cosine of the arcsine of x as an algebraic expression in x. So I need to have cosine of the arcsine of x equal to, and on the other side, I've got to have x's only. That's what that means. So let's see. Because we're talking about the arcsine here as our initial function, well, we know that those outputs for the arcsine, regardless of what axis we give it, has to be in between negative pi over 2 and pi over 2, just like we did in that last little part of the previous problem. And so this means my angle, we usually just call this theta, not a function of x, but some sort of theta. That means theta has to also be bounded by those values. And I'm thinking now I can write an expression that theta is equal to the arcsine of x. And now we can kind of rethink this relationship. If this is true, then x must equal the sine of theta. And now I feel like I've got some stuff to work with here. This x, or this sine of theta, based on the original construct of the problem, has to be positive. So this means I am operating here in that first quadrant. And now I know how to draw my triangle. I'm going to put my theta mapping into quadrant 1. I'm going to drop my perpendicular. And then I'm going to use this information. It says the sine ratio for theta is x over 1. Well, this is the length of the side opposite over the hypotenuse. And now all I need to do is figure out this missing sign, and I can write my cosine of this value. And I'm going to do that just like we did in the previous problem. I'm going to use the Pythagorean theorem. This is 1 squared minus x squared. Take its square root. So my expression is 1 minus x squared. Therefore, the cosine of the arcsine of x is just going to be my side adjacent over my hypotenuse. And we would just probably wouldn't write the 1 as the denominator. We would just write it like this. Kind of fun. This is a little preview of something that you will see in calculus when we start working with derivatives of our inverse trig functions.